Welcome to G Fun Facts Online. Today, we are traveling to the high-altitude peaks of the Chilean Andes to discuss a machine that promises to change our understanding of the universe forever. The Atacama Desert in Chile is one of the driest places on Earth. The air there is so thin, and the skies are so impossibly clear, that the Milky Way literally casts a shadow on the ground. It is the perfect place for astronomy. And right now, atop the flattened peak of a mountain called Cerro Pachón, a new era has begun. The dome of the Vera C Rubin Observatory has opened, and inside sits a technological titan known as the LSST Camera. This is not just another telescope. For centuries, astronomy has been a discipline of static snapshots, taking long exposures of single objects frozen in time. The Rubin Observatory changes that paradigm entirely. It is a time machine and a motion picture camera combined, designed to capture what we call the transient sky. This is a universe that is constantly moving, flickering, exploding, and evolving. At the heart of this observatory lies the LSST Camera, a device of such staggering complexity that it redefines the limits of human engineering. It is the largest digital camera ever constructed for astronomy, a 3.2-gigapixel behemoth the size of a small car. To put its power into perspective, this camera is capable of spotting a golf ball on the moon from the surface of the Earth. In this episode, we are going to explore the engineering marvel of this camera, the scientific revolution it is currently unleashing, as the full survey begins here in early 2026, and the profound mysteries of the dark universe it aims to solve. To understand the scale of the LSST camera, we have to abandon standard comparisons. It is not simply better than previous cameras, it is in a different weight class entirely. The camera body itself is roughly 5.5 feet by 9.8 feet, and it weighs a crushing 6,200 pounds. That is nearly 3 tons of precision equipment hanging off the back of a telescope. The retina of this mechanical eye is its focal plane. Unlike the sensor in a high-end commercial camera, which might measure 36 millimeters across, the LSST focal plane is a circular array spanning 25 inches or 64 centimeters in diameter. It is composed of 189 individual charge-coupled device sensors, or CCDs, each offering 16 megapixels of resolution. These sensors are not mounted individually. They are grouped into 21 modules called rafts. Each raft is a square tower that houses 9 sensors, along with their dedicated electronics. This modularity was a critical design choice. If a sensor were to fail during the camera's decade-long mission, a single raft could theoretically be serviced. Although the procedure is so delicate, it is reserved only for absolute emergencies. The engineering tolerance required to assemble this focal plane is mind-bending. The surface of the 189 sensors had to be flat to within a fraction of the width of a human hair. Any deviation beyond that would throw the telescope's incredibly fast optics out of focus. The gap between the sensors is a mere 100 microns, meaning the dead space in the images is effectively negligible. To capture an image, the camera operates in a step-and-repeat mode, covering the entire southern sky every 3 nights. But the sensors are only part of the story. Light entering the camera passes through 3 massive fused silica lenses, designated L1, L2, and L3. The first lens, L1, is the largest high-performance optical lens ever fabricated, measuring 5.1 feet in diameter. The raw glass for this single component took 5 years to shape and polish. The optical system is designed to provide an exceptionally wide field of view, covering 9.6 square degrees. To visualize that, a single exposure covers an area of the sky equivalent to 40 full moons arranged in a grid. This wide field is essential for the survey's speed. Without it, mapping the entire sky would take decades rather than days. Between these massive lenses sits the filter exchange system. This is a robotic carousel that holds 5 massive optical filters, each weighing nearly 90 pounds. These filters allow astronomers to slice the light into different colors, from the ultraviolet to the near-infrared. There is even a mechanism to swap a 6th filter into the carousel during the day. This automated dance happens continuously throughout the night, with the changer swapping filters in under 2 minutes to match the scientific goals of the moment. To detect the faint whispers of photons from galaxies billions of light-years away, the sensors must be kept in absolute darkness and extreme cold. The focal plane is housed inside a cryostat, a vacuum chamber that keeps the sensors cooled to -100 degrees Celsius. This deep freeze suppresses dark current, which is the thermal noise that would otherwise drown out the signals from distant stars. However, the readout electronics generate a considerable 100 watts of heat. This heat must be wicked away efficiently without causing vibrations that would blur the images. This is achieved through a newly developed clean refrigerant system that circulates fluid through the back of the raft towers, a feat of thermal engineering that took years to perfect. When the shutter opens, the LSST camera acts less like a telescope and more like a fire hose of data. It takes a 15-second exposure, reads out the data in 2 seconds, and moves to the next patch of sky. This cadence generates approximately 20 terabytes of raw data every single night. Over the 10-year survey, the archive will swell to 60 petabytes of images and catalogs. But the most time-critical aspect of the Rubin Observatory is its transient alert system. The universe is full of things that go bump in the night: supernovae, variable stars, asteroids, and gravitational wave events. Many of these are short-lived. A flash of light might last only minutes. To catch these fleeting events, the observatory has set a grueling requirement of 60 seconds. From the moment the shutter closes on an image, the system has exactly 1 minute to transfer the massive image file from the summit in Chile to the data facility in the US, process the image to remove instrumental artifacts, and then subtract a template image. A template is simply an older image of the same spot in the sky. By subtracting the old from the new, the computer reveals only what has changed. It then identifies any new sources based on changes in brightness or position and sends out an alert to the global astronomical community. This pipeline effectively runs a spot-the-difference game on a cosmic scale, millions of times a night. Because no single human, or even a large team, can read 10 million alerts per night, the Rubin Observatory relies on community brokers. These are third-party software systems that ingest the full stream of alerts and act as a filtering layer. An astronomer interested in supernovae does not want to see alerts for asteroids. The broker uses machine learning algorithms to classify the alerts in real time, flagging one alert as a likely supernova and another as a near-Earth object. This automated infrastructure changes the day-to-day life of an astronomer. Instead of traveling to a telescope to take data, they wake up to a filtered feed of targets delivered to their inbox, ready for follow-up observation. Now, let's look at the science. The Rubin Observatory was designed with 4 primary scientific pillars. The first is probing dark energy and dark matter. The dark universe makes up 95% of the cosmos, yet we have no idea what it is. Dark matter holds galaxies together, while dark energy pushes the universe apart. The LSST camera is the ultimate tool for something called weak gravitational lensing. As light from distant galaxies travels to Earth, it passes by massive clumps of dark matter. The gravity of this dark matter bends the light slightly, distorting the shape of the background galaxies. By measuring these minute distortions in the shapes of billions of galaxies, astronomers can map the 3D distribution of dark matter across the universe. Furthermore, by seeing how this distribution has changed over billions of years, they can infer the properties of dark energy. The sheer volume of galaxies, estimated at 20 billion, will reduce statistical errors to near zero. The second pillar is taking inventory of the solar system. Before Rubin, we had identified roughly 800,000 asteroids. The LSST is expected to increase that number to over 5 million. This includes identifying potentially hazardous near-Earth objects larger than 140 meters, mapping the main belt asteroids between Mars and Jupiter to understand the formation of the solar system, and charting the icy Kuiper belt objects beyond Neptune. Deep in these outer reaches, some objects exhibit strange orbital clustering, suggesting they are being shepherded by the gravity of a massive, unseen planet known as Planet 9. Searching for Planet 9 is like looking for a needle in a haystack, but simulations suggest that if it exists, Rubin has a 95% chance of detecting it. The third pillar is the transient optical sky. This is the cinema aspect we discussed. By imaging the sky repeatedly, Rubin creates a time-lapse movie. This will allow for the discovery of millions of supernovae, helping us understand stellar life cycles. It will also help us spot kilonovae, the mergers of neutron stars that produce gold and platinum. Rubin's wide field of view increases the chance of catching the optical flash of a gravitational wave event. The fourth pillar is mapping the Milky Way. Rubin will map the position and brightness of billions of stars in our own galaxy. This will allow astronomers to conduct galactic archaeology, tracing the history of the Milky Way by identifying streams of stars that were torn from smaller dwarf galaxies that our galaxy cannibalized billions of years ago. Beyond these 4 pillars lies the exotic frontier. This is where the unknown comes into play. One major area of interest is interstellar objects, or ISOs. In 2017, the object Oumuamua zipped through our solar system, followed by Comet Borisov in 2019. These were visitors from other star systems. We now know that interstellar space is likely teeming with these ejected wanderers. The LSST is a game-changer here. Recent models predict it could detect anywhere from a few to 70 interstellar objects per year. We are already seeing the fruits of this new era. In July 2025, the Atlas survey discovered a new candidate designated 3I/Atlas. With Rubin now online, we can track objects like 3I with unprecedented precision. Calculations show that in January 2026, This object aligns with the Earth-Sun axis, providing a rare opportunity for Rubin to measure its opposition surge, a brightening effect that reveals surface texture. Rubin will likely also find dark comets, objects that do not off-gas like traditional comets, but pass through on hyperbolic orbits, invisible to smaller telescopes. Another exotic phenomenon is tidal disruption events. Occasionally, a star wanders too close to a supermassive black hole and is shredded by tidal forces in a process vividly termed spaghettification. As the stellar debris rains down onto the black hole, it flares brightly. Before Rubin, we found these events largely by luck. Now, we expect to find between 3,000 and 8,000 of them per year, allowing us to study the demographics of black holes and dwarf galaxies. Then, there are fast radio bursts, or FRBs. These are millisecond-long blasts of radio energy from deep space. Finding their optical counterpart, a flash of visible light accompanying the radio burst, has been a holy grail of the field. Rubin's rapid cadence makes it one of the best hopes for catching an FRB in the act, in optical light. Building this machine was a saga of endurance. The contract to build the 189 sensors was split between two vendors to ensure redundancy. The sensors are deep depletion CCDs, much thicker than standard chips, which allows them to capture more near-infrared light. However, thick chips are harder to manufacture and more prone to pixel blooming. The project was not without its heart-stopping moments. In 2023, during final integration at SLAC National Accelerator Laboratory in California, a main water supply line in the cleanroom burst. Water sprayed near the camera housing. The team executed an emergency shutdown. The camera was shrink-wrapped in protective plastic, but the humidity spike was a major threat. A subsequent investigation showed that while the camera was safe, a cryostat vacuum pump had failed, and a feed-through leaked. It took months of painstaking testing to recertify the system, delaying the shipment to Chile. Finally, in mid-2024, the camera was packed into a custom-built, shock-absorbing shipping container and flown to Chile. It was driven up the winding Andes Mountains to the 900-foot summit. The installation in early 2025 was a millimeter precision operation, where the 3-ton camera was inserted into the center of the secondary mirror assembly with less than an inch of clearance on either side. The Rubin Observatory represents a paradigm shift in the culture of science, specifically regarding the democratization of data. In the past, telescope time was a precious resource, hoarded by principal investigators. If you applied for time on the Hubble, the data was yours exclusively for a year. Rubin has no proprietary period for its alert data. The moment an alert is generated, it is public to the world. The nightly images are available to all data rights holders immediately. Because the data volume is so massive, reaching petabytes, you cannot download it to your laptop. You have to take your code to the data. The Rubin Science Platform is a cloud-based ecosystem where astronomers log in and run queries remotely. This levels the playing field, giving a student at a small university the same access as a professor at a top institution. As we stand here in early 2026, the full survey is just spinning up. The first data preview releases have already teased us with images of dazzling depth. Over the next 10 years, the LSST camera will record the greatest movie ever made. It will catalog 37 billion stars and galaxies. It might find the hazardous asteroid that has our name on it, or reveal the existence of a 9th planet in our backyard. But the most exciting discovery is the one we haven't predicted. We are opening the shutter on the unknown. Welcome to the era of the Rubin Observatory. The show is about to begin.